how to solve a differential equation using Frobenius method. There's 5 steps you want to follow. The first step is that you want to determine the singular points. The second step is that you want to determine whether these are regular or they are irregular singular points. The third step is you want to find the indicial equation. The fourth step, you want to use Frobenius method using the power series expansion to solve the differential equation for y1 and y2. And the fifth step is that you want to find the general solution. So let's get started. The first step is to determine the singular points. It's very easy to do that in this equation because you look at whatever the coefficients and the x terms are in front of the highest derivative. So 3x squared is in front of y double prime, which means x equals 0 is a singular point. But now step number 2 is that we want to determine whether x equals 0 is a regular or if it's an irregular singular point. And the way we do that is by dividing the entire equation by 3x squared. So we have y double prime minus x divided by 3x squared is 1 over 3x y prime plus the quantity x squared plus 1 divided by 3x squared times y equals 0. The way you determine whether they are regular or irregular singular points is that if the singular point appears to the first power when it's in the denominator of the first derivative, and it appears at max to the second power in the denominator of the 0th derivative, then it is a regular singular point. So since x appears to the first power in y prime and x appears to the second power in y to the 0th derivative, it is a regular singular point. So step number 3 is to find the indicial equation. The way you find the indicial equation is you find p sub 0 and q sub 0. Remember, this is capital P of x and this is capital Q of x. So the way you find the indicial equation is with this formula right here. R times R minus 1 plus P sub 0 times R plus Q sub 0 equals 0. So now we have to find P sub 0 and Q sub 0. The way we find these two equations, the way we find these two terms is like so. P sub 0 equals the limit as x approaches the singular point. The singular point here is x equals 0. So P sub 0 equals the limit as x approaches 0 of x minus the singular point. X naught is the singular point. If this was anything other than 0, then you would write it here. But since x naught equals 0, I'll write this here, x naught equals 0, it's simply x minus 0, which is just x. So x times capital P of x, where capital P of x is this term minus 1 divided by 3x. So P sub 0 is the limit as x approaches 0 of x times negative 1 over 3x. The x's cancel out. The limit as x approaches 0 goes away because there is no x term. So P sub 0 is negative 1/3. Now Q sub 0 is going to be the limit as x also approaches the singular point, x equals 0, times this x minus x naught squared q of x. X naught again is 0, so it's simply the limit as x approaches 0 of x squared times capital Q of x, which is x squared plus 1 divided by 3x squared. The x squared terms cancel out, and we're left with the limit as x approaches 0 of x squared plus 1 divided by 3. As x approaches 0, the limit approaches 1/3. I hope you can see that from there. You can, because I set the camera up earlier. So Now we have P naught and Q naught, so we're on step 3, the initial equation. Let's write it down here. R squared minus R plus P naught times R. P naught is negative 1/3 times R plus Q naught, which is 1/3, equals 0. So now let's go ahead and solve this just like we would any other quadratic equation. Minus R minus 1/3 R is minus 4/3 R plus 1/3 equals 0. Now let's use the quadratic formula here. It's minus b plus or minus the square root of b squared minus 4ac divided by 2 times a. I'm actually not going to use the quadratic formula. I'm going to use the Poisson-Low method. If you don't know how to use that, then I would suggest looking it up on YouTube because it's so much easier than using the quadratic formula. As a matter of fact, one of these days I might make a video on how to do it because I think it's so useful. So instead of using this, I'm going to use this formula. Minus b over 2 minus u minus b over 2 plus u equals c. And c is the same as that you would put in this equation, and b is the same as you would put in this equation. U is another variable that you're going to solve for. Basically, you can consider u to be the same thing as x, and you want to solve for x, but it's just solving for u. So let's plug in the numbers. B is minus 4/3. So minus 4/3 is positive 4/3 divided by 2 is going to be, I'll just write it all out. That way you can see it. Minus 4/3. I should have written minus 4/3 over 2 minus u times minus 4/3 over 2 plus u equals c, which is 1/3. So minus 4/3 is going to be positive 4/3 divided by 2 is 2/3 minus u, and then 2/3 plus u equals 1/3. So when we multiply this out, this is going to equal 4 over 9 minus u squared equals 1/3. And then we're going to solve for u squared. So u squared equals, add u squared minus 1/3. So we have 4 over 9 minus 3 over 9, which is 1 over 9. U equals 1/3, and it doesn't have to be positive or negative because you see you're going to plug it back into this equation here. Plug it back into this equation here. So you already have a minus u and you have a plus u. So we have R1 equals the bigger root. So we have 2/3 plus 1/3 is 1, and then R2 is 2/3 minus 1/3, which is 1/3. So those are the two roots of the equation that we have here. So I'm going to erase this, and I'm going to write it up here. I think that's a decent start for the initial equation there. R1 equals 1, R2 equals 1/3. So now that we have the initial equation done, now we're going to use Frobenius' method to solve the equation for y1 and y2. So the method is y equals the infinite sum from 0 to infinity, obviously, c sub n times x to the n plus r. Y prime is the infinite sum. N goes from 1, c sub n, n plus r, x to the n plus r minus 1. I want to say something real quick about the indices, because when I first learned this method, the power series solutions for differential equations go up by 1 whenever you differentiate, because if you were to expand the infinite sum and then take the derivative of it, the 0th term always goes away, so you shift the index up by 1. When I first learned the Frobenius method in the book, they didn't shift the index up by 1. They simply kept it at n equals 0 for y, y prime, and y double prime, and it stayed n equals 0, n equals 0, and n equals 0. And if you use the initial equation before you use the Frobenius method, then you don't have to keep the indexes the same. You can shift them up by 1 the same way you would a power series expansion, and then you don't have to, because the reason you keep it at n equals 0 is because in the process of doing the Frobenius method, you will come across the initial equation, because you set the entire coefficient of the lowest power of x equal to 0, meaning if you have x to the negative 1, then you set everything in front of x to the negative 1 equal to 0, and that's going to give you your r terms, r1 and r2. But since we already have r1 and r2, we don't have to worry about having a lowest power of x with every coefficient in front of that being set equal to 0. So that's why we can shift the indices up every time we take the derivative. So y double prime then is equal to the infinite sum as n goes from 2 to infinity, c sub n, n plus r minus 1, x to the n plus r minus 2. And now we can plug this all back into the equation here. So 3x squared times the infinite sum as n goes from 2 to infinity of c sub n, n plus r minus 1, x to the n plus r minus 2, minus x times the infinite sum, n goes from 1 to infinity, c sub n times n plus r, x to the n plus r minus 1, plus x squared plus 1 times the infinite sum as n goes from 0 to infinity of c sub n, x to the n plus r equals 0. And now we just distribute all of this stuff out. So it's going to be the infinite sum, n goes from 2 to infinity, c sub n, 3n plus 3r times n plus r minus 1 times x to the n plus r. Because x squared times x to the n plus r minus 2 is going, the 2's are going to cancel out. They're going to add negative 2 plus 2 equals 0. Then we have x times this term, x times x to the n plus r minus 1 is x to the n plus r. So it's going to be n goes from 1 to infinity, c sub n times n plus r times x to the n plus r. Then we distribute these out. X squared makes this x to the n plus r plus 2. So we have the infinite sum as n goes from 0 to infinity, c sub n times x to the n plus r plus 2, plus another infinite sum, because the 1 has to distribute out as well. So it's n goes from 0 to infinity of c sub n times x to the n. All of this equals 0. Now at this point, we can factor out the x to the r from all of these terms, because that's just how we do it. That's just the step that we're going to continue on doing. We're going to factor out x to the r from all of these terms, and then we're going to be left with the power series that we can simply change the indices and solve for k. So it's the infinite sum again, n equals 2, c sub n, 3n plus 3r, n plus r minus 1, x to the n minus infinite sum, n equals 1 to infinity, c sub n, n plus r, x to the n plus infinite sum, n equals 0, c sub n, x to the n plus 2. These problems do take a long time to do. That's why it's so frustrating to mess up on these problems, because when you mess up, you got to spend 30 minutes going back through your work, if not more time than that, going back through your work. And it's so frustrating whenever you get these problems wrong, because usually it's just one number that you missed. I did that earlier whenever I was trying to solve this problem earlier. During the initial equation, I accidentally didn't include the 3 whenever I did the capital Q of x, and so it was simply the limit as x goes to infinity, the limit as x goes to 0 of x squared plus 1, so I got Q naught equals 1 instead of Q naught equals 1/3. So I had to go back through and then fix the entire equation from there. It's really frustrating. So I can go fast on this problem because I already went through this problem before, but if this is your first time going through the problem, if it's your first time going through a problem, then just go slowly. Make sure you get all your numbers, your signs correct, because one sign and one number can mess up the entire equation. So we've done this, we've done this, we've done this. So now we're on this one, plus infinite sum, n goes from 0 to infinity, c sub n, x to the n, and this is close bracket equals 0. So now the step that I like the most is setting all of the indices equal to k. K equals n equals k. K equals n equals k. K equals n plus 2, n equals k minus 2. K equals n equals k. So we have x to the r times everything else once again. This time, k equals 2 because n equals 2. And then we have c sub k times 3k plus 3r. Then we have k plus r minus 1, x to the k, minus another infinite sum, k equals 1, c sub k, k plus r, x to the k, plus another infinite sum, k equals 2, because 0 plus 2, c sub k, x to the k, nope, that's actually wrong, c sub k minus 2 times x to the k, plus another infinite sum of k equals 0, c sub k, x to the k. All of this equals 0. So now from here, we want to make all of the indices the same. So these two are already 2. So we want to take one term from this and 2 terms from this. That way this can equal 2 and this can also equal 2, which means we're going to have 3 terms left over. So let's go ahead and write this down one more time. Probably not one more time, it's probably going to be a couple more times than that. C sub k, 3k plus 3r, k plus r minus 1, x to the k, minus infinite sum. I'm going to change this to 2 right now, but we're going to come back to it and we're going to collect the term from it. C sub k, k plus r, x to the k, plus infinite sum, k equals 2, c sub k minus 2, x to the k, plus another infinite sum, k equals 0, nope, k equals 2, c sub k, x to the k, and now we're going to collect these terms. So c sub 0 is, well, when k equals 0, we have c sub 0 times x to the 0, which is just plus c sub 0. Then we have c sub 1 times x, so plus c sub 1 times x to the 1. And then we come over here, and then we have minus c sub 1 times 1 plus r, times x, close bracket, equals 0. This is normally the part where you would have a negative x and then you would solve the lowest, you would set everything that is the coefficient of the highest power of x equal to 0, and then you would get the initial roots from there. But you don't have to now because we already have the initial roots. So as a matter of fact, you can just call C1 0 because that's what C1 is. If you take these terms and then you collect them together, so if you have C1 times x times 1 minus 1 plus, or it's going to be minus 1 plus r equals 0. If you divide by C1 and x, or if you divide by x, really, if you divide by x and you solve for C1, it's going to equal 0, because you're going to have 1 minus 1 equals 0 minus r. If you divide by x minus r, then you get C1 equals 0. So C1 is going to be 0. C0 is not going to be 0, and we'll find that out later on whenever we do the entire equation. So now that we have this all rewritten out, we have all the k terms the same, the next step is to combine the summations and then factor out an x to the k. So we have, I'm going to write it right here, x to the r times the infinite sum, k goes to 2 to infinity. And now we're going to do a bracket because we're going to copy all of this down. C sub k times 3k plus 3r times k plus r minus 1 minus c sub k times k plus r plus c sub k minus 2 plus c sub k, x to the k, plus c0 plus c1x times minus r equals 0. And that is what this right here is what we're going to set equal to 0, because we don't have to worry about C0 and we don't have to worry about this because we already have the initial roots right there. So let's set the inside of this equal to 0. So it's going to be C sub k, 3k plus 3r, k plus r minus 1 minus c sub k, k plus r, plus c sub k minus 2 plus c sub k equals 0, 4, k equals 2, 3, 4, dot, 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 all the way to infinity. Now this step is we have to solve for the highest subscript of k, which is going to be this term, and this term. So let's subtract c sub k minus 2 from both sides. Excuse me. We're going to subtract c sub k minus 2 from both sides, factor out a c sub k from all of these terms, and divide negative c sub k minus 2 by all of these terms here. So it's going to look like this. C sub k equals a big fraction, 3k plus 3r, times k plus r plus 1 minus 1 minus k minus the quantity k plus r. Remember the parentheses there because that minus sign distributes to the k and to the r. So you have to put parentheses there. Plus 1. then minus c sub k minus 2. Because these terms are from the first c sub k right here, this minus k minus the quantity k plus r is this term right here, and then c sub k makes that factor a 1 right there. And this is still true for k equals 2, 3, 4, dot, dot, dot. So now we have two roots. So we're going to have two different sets of infinite series. The first one is going to belong to root 1, and the second one is going to belong to root 1/3. So let's say that we're going to erase this. We're going to erase this. And then we're going to write r equals 1. When r equals 1, c sub k equals 3k plus 3 times k, 1 minus 1 is 0, minus k plus 1 plus 1. I'm going to distribute that out. So we have minus k minus 1 plus 1 is just minus k, minus c sub k minus 2. And that's true for all k. So let's say we have k equals 2. Now we're going to begin our first term here. When k equals 2, c sub 2 equals negative c sub 0 times, or divided by, 3 times 2 is 6 plus 3 is 9 times 2 is 18 minus 2. So we have minus c sub 0 over 16. When k is 3, we have c sub 3 equals, well, I won't even have to write all of this out, because if you remember that c sub 1 is 0 because of the work that we did earlier in setting it equal to 0, we have negative c sub 1 over some denominator. Whenever you work this out, it's going to be 9 plus 3 is 12 times 3 is 36 minus 3 is 33. So negative c1 over 33. But c1 is 0, so c3 is 0. Then we might have some kind of pattern going here. So let's go to k equals 4. We have c sub 4 equals negative c sub 2, which is this term right here, divided by 3 times 4 is 12, plus 3 is 15, times 4 is 60, minus 4. So we have negative 1, because I'm gonna change this c sub 2 into this term right here. Negative 1 over 56 times negative c sub 0 over 16 is positive c sub 0 over, what did I get that one to be? 896. And whenever we go to c sub 5, c sub 5 is going to equal negative c sub 3, which is 0. So the pattern is going to be every even subscript is going to equal a number, which is c sub 0. So we're going to factor out the c sub 0. And then every odd subscript is going to equal 0 because c sub 1 equals 0. So that's enough terms for now. So we have then that y sub 1 of x is equal to the infinite sum as n goes from 0 to infinity, c sub n times x to the n plus r equals x to the r times c sub 0 plus c1x plus c2x squared plus c3x cubed plus dot dot dot. So x to the r is x to the 1, y1 of x equals x to the 1 times c0. Now c0 is going to be c0, c1x is 0, c3x is 0, c2 is going to be negative c0, so we can factor out a c0 here, and every term that has a c0 in it is going to turn into 1. So we have 1 plus c2x squared. c2 is negative c0, so it's minus x squared over 16. c4 is going to be positive c0 over 896, so it's positive x to the 4th over 896 plus dot dot dot. And that is y sub 1 of x. So now we need to find y sub 2 of x. In order to find y sub 2 of x, we have to change the r value to 1/3. So instead of r equals 1, we have r equals 1/3, which will change this equation. We'll change this equation to 3k plus 3r is 3k plus 1 times k plus 1/3 minus 3/3 is minus 2/3 minus k minus r is 1/3 plus 3/3 is plus 2/3 minus c sub k minus 2. So now we have a different recurrence relationship with a different value of r. So now we can start solving for this recurrence relationship. Whenever k equals 2, c sub 2 equals negative c sub 0 over 3 times 2 is 6 plus 1 is 7 times k minus 2/3. Well, when 2 minus 2/3 is 6/3 minus 2/3, which is times 4/3, minus k, which is 2 plus 2/3, which is minus 4/3. So 7 times 4 is 28, minus 4 is 24, divided by 3 is 8. So negative c sub 0 divided by 8. Next is k equals 3. So we have c sub 3 equals, again, this is 0 because c sub 1 equals 0. And we're going to have negative c sub 3 minus 2, which is c sub 1, which is 0. So again, we can write this as 0. Then we have c sub 4 equals negative c sub 2, which is this term right here, divided by 3 times 4 is 12 plus 1 is 13 times 4 minus 2/3 is 12/3 minus 2/3 is 10/3 minus 12/3 plus 2/3 is minus 10/3 equals negative 1 divided by 13 times 10 is 130 minus 10 is 120 divided by 3 is 40 times negative c sub 0 over 8 is c sub 0 over 320. And that's good enough for now, because if we go to c sub 5, then c sub 5 is going to equal negative c sub 3, which is 0. So we're going to have the same repeating pattern of positive subscripts and even subscripts is going to yield an answer, and then odd subscripts are going to yield a 0. So we have y sub 2 of x is going to be x to the r, which is x to the 1/3, times c sub 0 is, again, we can factor that out as a 1. C sub 1 is going to be 0, so that's going to go away. C sub 2 is minus C sub 0 over 8. We're going to factor out the C sub 0. So we're going to get x squared over 8 plus C sub 3 goes away. C sub 4 is positive C sub 0, which we're going to factor out. So it's x to the 4th over 320 plus dot dot dot, and that's going to continue forever. So those are y sub 1 and y sub 2 using Frobenius' method. So now the fifth step is to put together the general solution. The general solution is the linear combination of is the superposition of two linearly independent solutions. You remember that from a couple of chapters ago. Y equals C sub 1 y1 plus C sub 2 y2. Well, y1 is this. So we have big C1 times x times the series 1 minus x squared over 16 plus x to the 4th over 896 plus dot 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 plus C sub 2 times x to the 1/3 times the series 1 minus x squared over 8 plus x to the 4th over 320 plus dot 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 all the way to infinity. And that is the final answer. So if you watched this whole video, thank you so much for watching. Just remember these 5 steps whenever you are solving with the Frobenius' method around a singular point. If x equals 0 is not the singular point, say if 3 was the singular point, then this entire equation would be different, because you instead of doing p of x equals x minus x naught times capital P of x, this wouldn't be 0. It would be, if x equals 3 was the singular point, it would be x minus 3 times P of x, which was negative 1 over 3x. And then you would multiply those out and it would be different. Of course, it doesn't work with this example because this is, I just picked that as a number, so obviously it wouldn't work out. But if you had a different singular point besides x not equals 0, then you would have to work it out a different way. But those 5 steps will pretty much get you to the answer every time. So if you watched this far, thank you for watching. Sorry it was such a long video, but please leave a comment if you have any questions or anything, and I'd love to be able to see if I can answer it. I'm also a student just like you, and I'm learning just alongside you. So thanks for watching.